let's see if I can, okay, hold on. First I share, then I make full screen. Or is it already sharing?
It is already sharing.
Perfect. Okay. All right. So this is visible, I hope. Okay. So let me start with this picture. So this is, I'm sure this picture is very familiar to at least a good fraction of you. And this is basically an image of the galactic center, the center of our own galaxy. And all these points here are basically positions of these stars, which are, the numbers or the names of which are noted here. So these are the orbits of these stars in the galactic center. And this is an image which has been acquired using the Keck telescopes in Hawaii, where they have been monitoring the motions of these stars for now almost 26 years. So it's taken these 26 years to actually now find the complete orbits of these stars. Now, this is an image which is obtained at the infrared, near infrared wavelengths, because the center of our own galaxy is extremely dusty. So you can't really probe the optical emission coming from the center of the galaxy. So immediately you can also see that, for example, this path, or some of these closed trajectories seem to be moving around something which is actually not visible in the infrared. So actually this is the center of a galaxy is actually visible at radio wavelengths, and there is a point source here called the Sagittarius A star, which of course you can't see here. And that is the center of the supermassive black hole in our own galaxy. So let's give look at some numbers, some interesting numbers, which explain or highlight the extreme speeds that are involved. So, for example, the S2 star is moving at speeds of 27 million kilometers per hour in an orbit, which has a diameter of 300 billion kilometers. Sorry, is there a disturbance I can? Okay. So 27 million kilometers per hour is the speed of the star, and it's moving in an orbit which has a diameter of 300 billion kilometers, and it has a period of 16 years. So if you just use the virial theorem, you now have the radius of the orbits, you have the speeds of these stars, so you can estimate the mass of the object around which these stars are moving, assuming Keplerian motion. And the mass of this central object, which is a kind of a dark object, can be derived using this very simple relation. M is equal to V square R by G. So you have V and R and the gravitational constant. And you can find that these stars are moving around a mass which is 4.1 10 to the 6 solar masses. And this is the mass of the supermassive black hole in our own galaxy. And so I would encourage everybody to, who's interested in this, to also look at these videos of actual stellar motions, which are provided at this ESO website. So I think this is a good start of this talk, because the nearest galaxy, or the galaxy in which we reside, has a supermassive black hole in the center. And all massive galaxies, actually, we know now, host supermassive black holes. So this work on the Galaxy Center was awarded the Nobel Prize in 2020 to three physicists and astrophysicists. So Roger Penrose is a mathematical physicist who the Nobel Prize was awarded for the discovery of the black hole formation. Or rather, he worked out the mathematics and found that black hole formation was a robust prediction of the general theory of relativity. And it was Reinhard Genzel and Andrea Ghez, both of who actually monitored the stellar motions in the center of our own galaxy for 2.5 decades using two different sets of telescopes. Andrea Ghez used the Keck telescope, while Reinhard Genzel used the VLT telescopes in Chile. Again, I put here a reference of an excellent article. If you're interested in learning more about this discovery, it's in the Quantum magazine. And this timeline on the right side actually has been picked up from this magazine, which shows, how this discovery was made all the way starting from 1916, where Carl Schwarzschild actually first discovered that the Einstein's theory of general relativity allows for a point of infinite density. And then, of course, the discovery of quasars, etc., which I will be talking about soon. The start of radio astronomy in the 1960s. Then Roger Penrose, his work was already very soon after the discovery of quasars in 1965. And in the 1990s, both Genzel and Guess started monitoring the stellar motions. And in 2020, they were awarded the Nobel Prize. So it's also good to see how science progresses, and it takes several decades before monumental discoveries can be made. Now, of course, we have the image of the central supermassive black hole in our own galaxy using the Event Horizon Telescope. And so you can see this is the dust lanes in our own galaxy, which you can see on a very clear night. And the very center of that, which is where the Sagittarius A star is now being resolved into this ring-like structure. So this orange color is, of course, is a false color image. And shows very clearly a kind of a hole in the center, which is the black hole shadow. And the ring around it is kind of expected to be the material which is moving at almost relativistic speeds around this black hole, probably in an accretion disk. And using just the Event Horizon Telescope image and also modeling and what we understand about the black hole radii Event Horizon using GR, a black hole mass has been estimated, which is very close to, so that's around 4 × 10⁶ solar masses, which is very close to what Genzel and Guess actually estimated with stellar motions. So this gives us confidence about the existence of the supermassive black hole. Now, let me go to another interesting discovery, which was in 2000, which was made in 2010. And this was the discovery of gamma ray emission from the Fermi Gamma Ray Telescope. So now on the left panel is this is the image of the galactic disk. And you can see here on the top and bottom, extending to several kiloparsecs, are these what are now called Fermi bubbles. And one way to explain the existence of Fermi bubbles is, which is shown here in the right side, is actually at some point maybe the black hole in our own galaxy was active, and it probably created some kind of a jet, and these jets are responsible for the gamma ray emission that we see even now above and below the galactic disk. So this is actually the very definition of an active galactic nuclei. So this is where we will start, and let me now, of course, go to a little bit of the historical background, and which will kind of put everything in a much better context. So the story starts actually not even in 1943, actually starts all the way in 1908. So here I've written a reference here. So this was a graduate student, a PhD student called Edward Farth, who used the Lick Observatory for testing. Actually, his PhD thesis was to make a spectrograph. And he obtained the spectrum of now well-known active galactic nucleus called NGC 1068, New Galaxy Catalog. That's what NGC stands for. And 1068 is the entry in that catalog number. And he already found that there were some, the galaxies that he looked at without realizing what they were, seemed to show a lot of emission lines. And this is one of the spectra of an active galaxy called NGC 5548. And the top and the bottom panels are basically showing the spectra of different, and you see all these lines up from different elements, that are producing these, the spectra. And the top and the bottom panels are the same spectra, but you can see that it's kind of zoomed in a little bit to show even more emission lines showing up, the ones which don't show very well on the top panel. So it was in 1943 that Carl Seyfert, who actually happened to be also a postdoc, found, he was working at the Mount Wilson Observatory in the US, and he found that there was a whole set of galaxies which seemed to show these emission lines. And so that is why, as a class, it was then that the study of these kind of galaxies started, and because of which these galaxies are now called Seyfert Galaxies. So Carl Seyfert basically carried out the first systematic study of galaxies, which showed these emission lines. And another peculiarity of these galaxies was that they also seem to harbor a central star-like nucleus. Okay, so so there was a few Seyfert, or rather few galaxies which had star-like nuclei, and they had spectra which were dominated by emission lines. And so these, these were studied in great detail. The spectra were also very interesting because you could see that there were very high excitation nuclear lines. For example, you can see iron 7, oxygen 3, neon 5, so very high excitation lines of some elements. And some of these lines, so you can see also here that there are narrow lines, as you just see from here, but of course we'll quantify that a little later. Also have under them broad bases in some cases, not all lines, but some lines have these broad bases. And these widths, or the bases, the broad bases, correspond to gas velocities of several thousand kilometers per second and up to 10,000 kilometers per second in some cases. So, so this is the start of the study of active galaxies. And here I show two images. One on the left is a normal spiral galaxy, where you can see it's a kind of a face-on galaxy. You can see dust lanes, etc. And you see that there is a central brightness. But on the right side, you see that the central brightness is actually superimposed. There is rather superimposed on it is a point source, as you can see from the diffraction spikes. So there is a very bright point source which is superimposed in the center of this galaxy. So these were the galaxies that Carl Seyfert studied in great detail. And this point-like nucleus is, yes?
Sorry to interrupt,
Yeah, no
but
worries.
the slide.
Talking about the black hole in our own galaxy, and then we went on to talk about the systematic work that was carried out by Carl Seyfert, and that was already in 1943. So these two images, these two panels are basically trying to make the case that I was mentioning about Carl Seyfert, that a fraction of the galaxies that they were looking at, especially spiral galaxies, and both these happen to be spiral galaxies, and a fraction of them seem to have a very bright point-like nucleus in the center, which you can see, of course, on the right side. And the brightness of this point source sometimes can be so large that it can completely outshine the light from the entire galaxy. So, you see the whole fuzz that you see in the gray, that's all the starlight from this galaxy. But the point source can be so bright that it can overwhelm all that. So a typical spiral galaxy, for example, has around 100 billion stars, so 10 to the 11 stars. But the luminosity of this point source can sometimes be 100 times larger. So in the cases where the point source is so luminous that you don't see much of the starlight from the galaxy, then if you, for example, took an image of this object, or like a short exposure, you only see the star. object. So that is the reason why some of these so-called active galaxies are called quasi-stellar sources, quasi-stellar objects, so star-like objects. Okay, the next slide. Right. So Carl Seyfert already found that these galaxies seem to have very prominent emission lines, which you see in the top right panel of one of the galaxies called NGC 4151. On the other side, on the other hand, there are four spectra of normal spiral galaxies on the left, and as you can see very clearly, the spectra is dominated by absorption lines. So this was the difference, that these so-called Seyfert galaxies seem to be, the spectrum was dominated by emission lines. And then the second thing was, of course, that these had star-like nuclei. So all such galaxies then came to be called Seyfert galaxies, but it was actually much later, till the start of radio astronomy, which kind of, really put a lot of focus on these kind of galaxies, because even after Carl Seyfert had made got a set of galaxies which were peculiar like this, they didn't still know what could be actually happening to produce these emission lines. So next slide. So the main drive for this kind of research happened after the discovery of quasars. So now this of course happened because of the start of radio astronomy and the start of being able to make radio interferometric images. And so there were these two pieces of work from two set of astronomers across the world. One was a group in Australia, which was headed by Cyril Hazard and Mackay and Shimmons, who were basically looking at now the radio sky, and they were using the technique of lunar occultation, using one of the biggest single dish telescopes that they had, which was the Parkes 210-foot antenna. And so actually I just wanted to highlight Cyril Hazard's name, because Cyril Hazard actually passed away just 9 days ago. So what these astronomers were doing was something very exciting. Even though they didn't actually have the resolution to, their radio telescopes didn't have the resolution, high enough resolution, because they were just using a single dish. Because of this technique of lunar occultation, they were actually able to get sub-arcsecond scale images of the radio sky. And that's because you kind of use the edge of the moon, which acts like a diffraction. So it's like a single slit, experiment. You can get fringes as the point sources, radio point sources, pass across the lunar limb. And because of which you can get much higher resolution information about radio sources in the sky. So they were particularly looking at this radio object called 3C273. 3C stands for the third Cambridge catalogue, and 273 is the entry. So what they could find was that using this lunar occultation, the this radio source seemed to be comprised of two very close by compact components. And then they were also, because they could get very accurate positions of these radio sources in the sky, they could also identify one of those components with actually what looked like a star. And it was a bright star. It was a 13th magnitude star. At the same time, in 1963, Martin Schmidt, who was looking at, this was in the Palomar telescope in the US. He was actually looking at the spectra of this particular source, so optical spectrum, and was able to identify a pattern of emission lines, which took him a little while to understand that they were actually the Balmer series of hydrogen, but at a very high redshift. So what they identified was the H beta, H gamma, H delta, and H epsilon lines at a redshift of 0.158. I'll show you the spectrum in the next slide. So these two pieces of discovery, which of course definitely happened after radio interferometry kind of came about, the 3C, the third Cambridge catalog, for example, was created, which was at 170 megahertz or so, using the Cambridge telescopes in the UK. And the high redshift was kind of what really increased everybody's, or rather attracted everybody's attention, because Carl Seyfert's galaxies were actually much, much more close by. But if you have, once you have a very high redshift object of like 0.158 at that time, that was very, very high redshift. All your requirements of extreme luminosity become even more extreme. Right? So you have to have a point source which is very, very luminous, very far away, which means it must be really luminous, in that, wherever it is. Of course, now we know that these redshifts are of cosmological origin, and they are because of the expansion of the universe. And this was, of course, the start of, or the discovery of quasi-stellar objects, QSOs, or quasi-stellar radio sources, which are short for quasars. I just want to mention that now with the JWST, the James Webb Space Telescope, the highest redshift quasars that we are finding are almost between, redshift 11 and 14, where the universe was just a few 100 million years after the Big Bang. So we are now finding, quasars as the universe was just formed. So it's quite exciting now with the JWST, but at that time in 1963, 0.158 redshift was unprecedented. Next slide. This is the spectrum which Martin Schmidt obtained. So on the top is the spectrum of 3C273, the top gray spectrum, and the bottom is the kind of the comparison spectrum of, showing how the Balmer lines, H beta, H gamma, H delta, in the kind of the laboratory frame, and you can see that he was able to identify these lines on the basis of their relative intensities and their separations. And so the redshift is, the emitted wavelength by minus observed wavelength divided by the observed, or I may be mistaken here. Is it observed or intrinsic? Okay, anyway. And the distance is obtained using the formula which is given here, speed of light into redshift by the Hubble constant. And that turned out to be around 470 megaparsec for the Hubble constant of 100 kilometers per second per megaparsec. So it's quite distant at that point. Next slide. Now we have much better images of 3C273, and so this slide shows that. On the left, you see a Hubble Space Telescope image of 3C273. So you can see very clearly this very, very bright point source, and you can in fact even see from the WIFPIC-2 image that there is a little bit of a kind of extended region, which is actually a jet in 3C273, which you can see in the optical. And in the left, exactly, thank you. And the right panel of the same image, you can see that when a coronagraph was used to kind of block the central bright emission, then you can see this fuzz beginning to appear. And this fuzz is actually the host galaxy of this black hole. And this happened to be an elliptical galaxy. So now we, of course, have a much nicer image of 3C273, and similarly in the radio, you have a much better image as well. So on the right, you see this blue emission that you see is, of course, a false colored radio image of 3C273. And the 2 point sources that Cyril Hazard and group had found are basically the center, the bright point source that you see where the cursor is pointed right now, which is the radio core, so-called the radio core. And the end of the jet, there is another bright feature, which is the hotspot. It's called the hotspot, which is another bright compact feature. So these two features were what Cyril Hazard and all had kind of inferred from their lunar occultation methods. Of course, now with nice interferometric images, you can see the connection between the core and the hotspot, and this connection is actually what is known as a radio jet. Okay, so now let's move to the next. Yeah, So now, of course, you have this image of active galactic nucleus called Hercules A in all its glory. The other name for the alternate name for Hercules A is 3C348. So now this is an image which kind of shows how AGN are multi-wavelength emitters. So this image is actually created by the three images on the right side, which shows on the top the visible light, which is what, of course, our eyes can see, and in this case, the Hubble Space Telescope could see. And then you see the host galaxy in the center. That fuzz that is actually is an elliptical galaxy. And then there's a point source inside that fuzz, which is actually a smaller galaxy falling into the elliptical galaxy. So there is something happening there. In the middle panel, the pink emission that you see is X-ray gas, X-ray emitting gas. And so this is an image which was acquired from the Chandra X-ray telescope. And immediately you can see again a couple of things. There is a bright point source in the middle, which is actually expected to come from very close to the black hole. We're still talking about the X-ray image now. And the X-ray image also shows these dark regions above and below, which are actually called X-ray cavities. Okay, so I will talk more about X-ray cavities in the coming slides. And so these are also very important. And then the bottom panel is the radio image of this galaxy. And you see a bright, or rather a faint point source in the middle, which is where the black hole is. And then you have these beautiful bipolar jets, which seem to be kind of, episodic or something, like they're just blowing bubbles. Of course, it's important to, and then the image, of course, the main image that you see in the center is kind of made from superimposing all these three different wavelength images. It is important to note the extent of this radio source. So with respect to the size of the host galaxy itself. So the host galaxy itself may be, just a few tens of kiloparsecs, but the sizes of these radio sources can be hundreds of kiloparsecs to even a megaparsec. So all this is coming from the central black hole that we also have, in the center of our own galaxy. So something is being, ejected from the central black hole, and that is what you see in this blue radio emission in this particular slide. Let's move on. Right. This is a slide to just mention that when astronomers got interested in these quasars and Seyfert galaxies, they found that the spectra typically showed two types. So type 1 was the one which showed, these emission lines which had these broad bases. And then you had the superimposed on that with these narrow lines. And so those are called type 1 Seyfert galaxies or type 1 AGN. And the bottom spectrum shows only the narrow lines, not the broad lines. And these were called type 2 spectrum, or rather type 2 AGN. Now, the narrow and broad basically just means their velocity widths or Doppler widths. And on the top, you have the broad lines can be a few hundreds of, rather few thousands of kilometers per second. And the narrow lines are typically few hundreds of kilometers per second in velocity widths. Okay, next slide. So given all the information that we have just presented, all the observational evidence, this is what is considered the zeroth order model, or the paradigm for an active galactic nucleus. So this cartoon, and so let's look at all the different components. So at the center, of course, is a supermassive black hole, which we, of course, have discussed in the previous slides. You also see the jets in yellow coming, being ejected from this regions close to the supermassive black hole. There is some material which is falling onto the black hole in an accretion disk. And for example, you already saw that in the Event Horizon Telescope image of our own galaxy. It also has, of course, been imaged for another AGN called M87. Which is, I will come to that in a later slide. And all these, small gray looking features are basically gas clouds The ones which are very close to the supermassive black hole and accretion disk are moving very fast because of the gravitational effects of the black hole itself. And these are the ones which give rise to very broad lines that you see in the spectrum. Further away, there are these gray clouds which are moving, of course, slower compared to the broadline clouds. These are the ones which give rise to the narrow lines. So this region, these different regions are called the broadline region and the narrow line regions. And there is this orange looking structure, which is likely to be, or it is rather, dust and molecular gas. And this region kind of hides your broadline region and the accretion disk from certain lines of sight. So for example, if the AGN is oriented in such a way that the torus, this is called the torus, dusty obscuring torus, if it hides the broadline region and the accretion disk, then you end up seeing only the narrow line clouds. So that would explain the type 2 AGN. And if the AGN is oriented in such a way that you see both the narrow line regions and the broadline region and the accretion disk, then you see a type 1 AGN. So this dusty torus actually has an opening, and then through the opening you can either see broad lines or not. So this is kind of our understanding of what is happening in the center of these galaxies, and this is what an AGN is. Okay, next slide. Yeah. So now let's talk a little bit about the radio mission that we've seen so far. They are like produced in very spectacular looking jets, and they are very, very large in extent. So this cartoon is showing that the emission is coming from synchrotron emission. Or the radio emission is synchrotron emission. And synchrotron emission is basically produced when you have charged particles, which could be electrons, positrons, protons, which are moving at relativistic speeds, speeds close to speed of light. And they are moving around magnetic field lines. And so that is a cartoon which is showing that. On the right is a spectrum that you get from such an assembly of charged particles, relativistic charged particles. And the spectrum is basically showing, the intensity versus frequency. So the main part of it, which is, the optically thin emission, which you can see, that slope, that is the signature of a synchrotron emission spectrum. And it has a particular slope called alpha. So alpha is, so I will talk about the alpha in the next slide, but basically this is how the spectrum, how the energy is distributed at different frequencies for the synchrotron emission. That's what the spectrum is. And at the bottom, I've given some references for reading more about synchrotron emission, and also some of the standard books which explain synchrotron emission in much greater detail. So next slide. Now I will just tell you a little bit of the details of this radio mission. So I've already mentioned alpha. So the alpha is the slope of the synchrotron emission that you see, and it is related actually to the slope of the energy distribution of the particles which are producing these photons. So now I'm showing you a plot which is basically giving you the distribution of the energies of the charged particles which are producing the synchrotron radiation. And so number of particles with energy E is proportional to the energy to the slope of minus P. And this P, which is the electron energy, or rather charged particle energy slope, that is related to the alpha by the relation that alpha is equal to P minus 1 by 2. Okay, so now this alpha that you typically observe, what you typically observe as when you take the spectrum of this, the jet emission that we have seen in the previous slides, that slope is typically around 0.7, and that relates to, or rather implies that the energy index of the charged particle should be around 2.4. And interestingly, that is actually observed, for example, for the cosmic rays which are charged particles moving in the magnetic fields of our own galaxy. That cosmic ray actually particles have an energy slope of around with an index of 2.4. So it's very interesting that, we are kind of confident with the fact that the synchrotron emission is coming from these kind of particles, and or rather the emission that you see in the radio is synchrotron emission. So because, that it has a slope of 0.7. Second thing to note is that synchrotron emission, the theory predicts that the degree of polarization, it will have, first of all, it will be linearly polarized, and the maximum degree of polarization is related by this formula to the P that we just discussed. And that gives, given the P of 2.4, the maximum fractional polarization that is expected from this synchrotron emission is supposed to be 75% or less. And this is actually also observed. So, so we know now very well, very confidently, that the radio emission that we see in these jets is from the synchrotron radiation. How do you produce these charged particles which have a slope like this, around 2 greater than 2 or 2.4, is through this process of diffusive shock acceleration, or DSA for short, which is also known as the first order Fermi acceleration mechanism, where you can basically energize particles through reflections around magnetic field inhomogeneities in the medium, which could be happening in various parts of these outflows. So that is an introduction to the radio emission that we get from these AGN. Next slide. Okay, so now let me tell you a little bit about the different radio structures that we see from these AGN. So on the left is an image of a galaxy called Cygnus A, and it is, you can see immediately from the comparing of the left and the right panels that there is a slight difference in the morphology of these two radio galaxies. In the left, you see a very collimated jet coming out from the AGN. But on the right, you see a jet which is not as collimated, little bit broad, and it kind of opens up to produce a plume-like structure. But on the left, you see that the jet stays collimated till the end, and it ends up in a region called the hotspot, which I also mentioned when I told you about 3C273. So these two types of radio galaxies are called, and they were first identified as such by two astronomers called Fanaroff and Riley. And so that's why these types of galaxies are called Fanaroff-Riley type of galaxies. So the left is a Fanaroff-Riley type 2 galaxy, and the right is a Fanaroff-Riley type 1 galaxy. So FR1 and FR2. Next slide. And after this whole research area took off, many more types of radio galaxies or radio sources were found. They were all AGN. And on the top, there are 4 pictures here. On the top panel, you see two radio images of 2 other types of AGN. I mean, one is on the left is a BLAC object, and on the right is a radio loud quasar. So now we know that all these FR1s, FR2 galaxies, BLACs, quasars are probably the same phenomenon, but at different orientations. So this is based, of course, not just on this image, but like you look at many properties of these AGN, which should be independent of orientation. For example, you may look at what is the total luminosity of the sources, what is the optical spectra like, what kind of galaxy are they living in, what kind of a galaxy environment they have. So based on all these, it is believed that FR1 galaxies, when they are pointed at small angles to line of sight, you obtain a BLAC object, and similarly an FR2 galaxy, which is oriented at a small angle to line of sight, gives you a quasar-like object. Next slide. Right. So now, since I've told you about FR1, FR2, I should also tell you a little bit about this. So the beautiful galaxies that we saw in the previous couple of slides, I mean, those were kind of the very spectacular cases of large jets, especially with respect to the size of the host galaxy itself. But most active galactic nuclei actually are not as impressive, but are more of the type that are seen here. This is NGC 1068. Remember, 1068 was the one where Edward Fath first obtained the spectrum and found to have, strong emission lines. So here in the right panel, the green emission is actually the optical light from the spiral host galaxy. And the red emission that you see is the X-ray emission from the hot gas. And then pink emission that you see is the radio emission. So the radio emission is very, very small compared to the host galaxy itself. And so now we understand these two types of sources as a radio loud object on the left and a radio quiet object on the right. So this was a work that Ken Kellerman and all and collaborators actually carried out, and you can see what I mean if you see the histograms that are plotted. So they basically just looked at this ratio of the total radio flux density to the optical flux density and found that when you plotted them for this Palomar QSO survey, there seemed to be two peaks, and the larger peak was the radio quiet objects and the smaller peak was the radio loud objects, and the division seemed to be at a value of R close to 10. So this is why R is equal to 10 is kind of taken as a dividing line between radio loud and radio quiet objects. But the thing to remember is that only 15% of AGN are radio loud. So the spectacular ones that I showed you in all the previous slides with large jets are actually only 15% of AGN. 85% of the AGN are not as impressive, but they are also active. They also have jets, but much smaller in extent. Okay, next slide. Right. So now I'm coming to, okay, this is already missing one thing, but I don't know why. Okay, it's missing some text, but doesn't matter. I can explain. So, okay, 1 second. I'm opening the equivalent one in my own thing. Yeah. So let's just very quickly talk about this technique of very long baseline interferometry, or VLBI. So this is a cartoon to show a VLBI experiment. So if you have light from a quasar, a distant quasar, and you are able to intercept the same wavefront from this quasar at two very widely separated radio antennas, then you can kind of make them work together like a single telescope, and this is the power of radio interferometry. So in telescopes like the GMRT, which is operated by our institute, the Giant Meter Wave Radio Telescope, in which all the radio telescopes are actually connected through optical fibers. If you actually take, for example, the GMRT and another telescope far away in a different continent, and you can make them work like a single telescope with the resolution which will be decided by the longest distance between the antennas, and that is also called the baseline. So once you can do these kind of experiments, you can arbitrarily increase baselines, and then you can arbitrarily increase the resolution. So if you remember, resolution is a function of directly proportional. So it's theta is equal to lambda by d. So either the lambda has to be small, or the d, which is the separation or the diameter of the telescope, in this case the baseline of the array, should be very large. So you can kind of keep improving the resolution of a radio array by using techniques like the VLBI. And basically the only thing that you have to make sure happens is that you actually always sample the same wavefront. And then when you kind of correlate signals from these antennas, they should have been recorded with a high enough time accuracy, to be able to correlate data. And therefore you need very highly accurate clocks. So you usually need a hydrogen maser clock, etc., to kind of get that kind of time accuracy to carry out VLBI. So let's go to the next slide, which kind of conveys this idea much better. So now this is actually the famous rather famous AGN called M87, Messier 87, and this was the one which was the first black hole shadow that was revealed by the Event Horizon Telescope. Okay, so there are 4 panels here. So let's just go through those. So now all the 4 panels are radio images, and the topmost is an image which was obtained by the Very Large Array. It's a radio telescope which has resolutions of a few arc seconds, very similar to the GMRT that we operate at NCRA. And you see nice jets. You can see lobe emission. It's called lobes, the diffuse emission which is not in jets. It's called lobe emission. And you can immediately see that this object seems to be like an FR1, FR type 1 radio galaxy, which is like, where the jets are not very collimated, but they kind of keep getting broader and broader, and then the produced plume-like radio emission. So this is like that. But if you look at the center of the VLA image, and then you look at the center with the high resolution array, which in this case is the very long baseline array, and you are able to resolve that point source that you saw in the previous image. And that point source now becomes another point source and a jet. So you are basically the point source that you saw in the previous image is kind of limited by the resolution of that telescope. But if you use a technique like the very long baseline array, interferometry rather, then you start resolving that emission from that point source. Then the third panel looks at the center, the core of the VLBA image, and uses what is known as the global millimeter VLBA array. And this is now, the second panel was at 43 gigahertz, and now this is at 86 gigahertz. So if you remember resolution being proportional to lambda by d, you are now going to shorter and shorter wavelengths, and thereby increasing resolution. So GMWave, of course, also resolves that so-called core emission into a core and a jet. But now you start seeing interesting effects. You start seeing what is known as the jet brightening, edge brightening rather. You can see that the two sides of the jet are brighter, but not so much the center of the jet. So this is also telling you some very interesting physics that is going on in the jets of these sources. And finally, you come to the Event Horizon Telescope, which is just a VLBI array, which operates at 230 gigahertz. So it's a bunch of some 7 radio telescopes which are working at 230 gigahertz, working together in a VLBI array. And then when you have such high resolution, then you are able to resolve all the radio emission going around the black hole itself, and you see the black hole shadow. And so this was the first EHT image that came out of this AGN called M87. Next slide. Right. So the reason for getting into this was because radio wavelengths, we are able to now perform interferometric experiments very routinely. And because of this, we are able to now get very, very high resolution. So the same has not been possible for optical telescopes, where the detection techniques are different. And it's also more difficult to actually carry out optical interferometry, even though this is now being carried out, for example, using the 4 telescopes of the Very Large Telescope, VLT, in Chile. And so interesting results are coming out, but not to the same resolution that is possible with radio at this juncture. So when you go to very high resolution imaging of the radio jets of these AGN, you start finding very interesting effects. And that's because you are now kind of probing the jet in the regimes where the special theory of relativity becomes important. And because of these, the jets being very fast, so they're relativistic, and because of which, and these are relativistic as they just launched from the black hole accretion systems, you start seeing interesting effects, like you see one-sided jets. You don't see the jet on the counterjet side. You see jet only on one side of the core. And then you see, second thing you see is that these jet knots, the points that you see, the red point sources are basically just the core of that AGN over several years. So it's given from 1992 to 1995. And then the jet emission, the bright point sources that you see are just portions of the jet, which seem to be moving very, very fast. So over 3 years, they have moved, let's say, 5 milliarc seconds. And then when you convert this into actual spatial scales and find the speeds of motion of these, you find that they seem to be moving at speeds greater than the speed of light. So that's called superluminal motion. So on the left panel is superluminal motion in one of the quasars, 3C279, And on the right side is superluminal motion in M87, one of the portions of M87's jet. So why is this happening? Let's go to the next slide. So even though it seems very counterintuitive to have speeds greater than the speed of light, there are very simple reasons once you consider the effects of the special theory of relativity, and then this work was actually first carried out by Blanford and McKee and others. And this cartoon is to show what kind of a configuration you would need to see this effect. So A is where where the observer is, and B is where the AGN is, and the theta is how these jets, which are coming from B, the jet knots are moving in that direction. Going towards B prime. So just with this geometry, you can find, so there's an equation given here, which is beta, which is just velocity by c, speed of light. T is for transverse motion. So that is how you see the motion across the sky, is basically equal to beta sine theta by 1 minus beta cos theta. And if you go to the previous slide once, yeah, so if you just have, for example, beta, which is the actual speed of the jet, and it is, let's say, 0.99, which means the speed of the jet is 0.99 times the speed of light. So it's never greater than speed of light, but it's close to speed of light. And if you have an orientation, the jet orientation is small, like 10 degrees, then you would have this beta transverse or beta apparent equal to 6.9 in the case of M87. So you have superluminal motion. So it's just the effect of these jets, which are very, very fast. They still have to be fast to produce this effect, and oriented at small angles to start showing these effects. So this is already telling you that the black holes eject, the black hole and accretion disk eject very, very fast jets, which then emit synchrotron radiation. And the motion of these jets itself is, the bulk motion of that is relativistic. Okay, next slides, next, and the next. Okay, so now I've come to the last part of my talk. Just this slide is actually the last, and then there's just one kind of example from the GMRT. So this is an important, I mentioned to you when we showed Hercules A about the X-ray cavities. And so we're coming back now to the X-ray cavities. So there are two things shown here. Of course, there are many other pieces of evidence which also, point towards this. But let's just look at these two pieces of evidence first. So on the left, the figure is basically plotting the mass of the black hole. So now there are many different, I didn't tell you about the techniques by which black hole masses are actually measured. I mentioned how it is measured in our own galaxy, which is stellar motion. But if you also have indications of gas motion through spectral observations, you can also get the black hole masses of external galaxies. So when you have the black hole masses of galaxies, and then what's plotted is black hole masses with respect to the luminosity of the bulge of the galaxy. This is the bulge of the galactic bulge, basically. And the second figure is stellar velocity dispersion, sigma E. Okay, so what is found is a very tight correlation, especially in the sigma E, where the stellar velocity dispersion is related to the mass of the black hole. But the important thing to remember is the mass of the black hole, even though it's very massive, the effects of it are actually only felt very close to it. So the gas clouds, which are giving the broad lines that you see in the spectra, those are affected, but not the stars in the galaxy bulge. It's very difficult to imagine how the galaxy bulge, which is much larger, how it's getting affected by how does it know about the mass of the black hole? And so the way we understand this is now that because this black hole is now throwing matter out in jets, etc., and that jets, for example, could be influencing the host galaxy somehow, moving the stars, compressing gas, causing star formation, increasing turbulence. And so that is the way you can explain this, this relation. And these set of explanations are called AGN feedback. How AGN is affecting the host galaxy. Now we come look at the right panel, and this is the center of a famous galaxy cluster called Perseus. This is and it's got a whole set of X-ray cavities, just like Hercules A. But when you look at the radio emission from this AGN, which is in the center of this galaxy cluster, you find that the radio emission seems to fill all these cavities. So this clearly tells you that the radio emission is the one, or the radio outflows are the ones which are causing these cavities in the X-ray gas in the galaxy cluster. So this is how the AGN seems to be not just limited to the black hole in the center, but it can go way beyond its own self and beyond the host galaxy and go all the way into the galaxy cluster and still start having effects. It moves gas around, it compresses gas, and then that is how it influences the much larger structures than itself. Okay, so now the last slide is a very interesting discovery that was made recently with using the GMRT telescope and also another telescope called LOFAR, or low frequency array, which is in the Netherlands and other places in Europe. The two images, now this is actually the discovery of the longest jet in coming from an AGN.
Hello.
I think she is
Got
muted.
muted.
Preeti, you are muted.
Sorry, when did this happen?
When you were
From this slide.
Okay, good. All right, sorry. So I don't know, many things are happening. Sorry. Yeah, so I was just saying that these two images are showing this extremely large jet and 7 megaparsec. I mean, a typical galaxy separation is like 1 megaparsec. And so this is the one of the largest jets that have ever been discovered in from an AGN. And both the GMRT and the LOFAR, or the low frequency array, were instrumental in kind of getting the extent of this galaxy. What is interesting is that because it's so large, it is actually covering a substantial portion of the cosmic void in which it resides. Okay, so if you're familiar with the large scale structure, studies of the universe, there are these filaments and voids, and voids, cosmic voids are places where there is a dearth of galaxies, for example. And so it's kind of covering 70% of the void in a cosmic void in which it resides. And so it's very likely that this kind of a galaxy, there must be many more of such AGN. And this is actually at a very high redshift, around 1 or something, very high, very in the early part of early life of the universe. It's probably from these galaxies that you're able to supply both charged particles and magnetic fields to the voids, to the galaxy void. So you're kind of really influencing the evolution of galaxies and the universe from these structures which are centered around supermassive black holes in the centers of galaxies. So I will stop here, and I'm happy we can have a discussion, a little bit of a discussion.
Thank you very much, Professor Preeti Kharb. If anyone has any questions for her, then you can take it up quickly. Yes, Samrat.
Good afternoon, ma'am. Thank you for
Hello.
the presentation. Yes, so I had a question about the very first slide which we saw. There was an equation there. Yeah, this slide.
Yeah.
There is this equation m equals to v square r by g. So my question is this equation applicable only to the stars orbiting the black hole, or is it in general applicable to any object orbiting another more massive object?
Yeah, so it is applicable to anything, any. This is just the Kepler's laws and Newton's laws of motion. So this is applicable to every situation.
Okay, so let's say if I have the radius and velocity of the moon, then it can give mass of the Earth.
So here you have to decide if the motion is Keplerian. First, you have to find out that, and if it's it's because of this gravity of the central object around which it is moving. Once those things are taken care of, you can.
Okay. Okay, ma'am.
Yeah.
Where R is the distance from the object, central gravitating object. We can quickly take up a couple of more questions if there are any. Okay, if not, then let's thank the speaker for her valuable time. Thank you, Preeti, very much.
Thank you so much, Kiran. I'm very sorry for all the disturbances that happened, but I think once you started, you did a good job. So hopefully
Yes.
this was conveyed.
There is one more question from Tanish
One
quickly.
more.
Yeah.
Yeah. Hello. Am I audible?
Yeah.
Yes.
Yeah. So, can you please go to that slide in which X-ray cavity was visible?
This one?
Next,
In which there was some.
this one? Yeah, this one has it, for example.
So, yeah, I just wanted to know what is the scale of these cavities. Like, are they extending beyond the usual galaxy limit? Are they going? So, yeah, what's the scale of
Yeah.
these things?
Yeah,
These
so
cavities.
exactly. So as you can see in this image itself, the scales of these cavities is much larger than the host galaxy. So this is definitely in the galaxy clusters. So these cavities are produced in the intercluster medium actually. So, but also sometimes you see cavities even on smaller scales. Even within the host galaxies, you can see cavities in some places or just smaller scales. But like this particular source, for example, in Hercules A and also Perseus A, the cavities are much larger than the host galaxies.
Yeah, Perseus is,
Yeah.
you know,
Okay.
these images are
Thanks.
to scale, right? All these images are to same scale. Okay, so thank you very much, Professor Preeti Kharb.
Okay. Thank you so much for
Was
inviting me. I'm very happy if you want to share the PDF files with anybody who's interested. Maybe that will help.
okay, great. Thank you very much. And it
Thank
was
you. Thank you.
wonderful
Thank you,
talk.
Preeti.
Yeah,
Thank you, Ayushi. Bye.
bye.